the concept of reverse probability. Welcome, everyone. Today, we are going to explore a fascinating and highly practical area of mathematics, the concept of reverse probability. Now, before we dive into the new material, let's take a moment to reflect on what we have already mastered. In our previous lessons on probability, we have spent a lot of time studying conditional probability. You'll remember that this is a powerful tool that allows us to calculate the likelihood of a specific event occurring, provided that we already know another event has taken place. It's all about updating our expectations based on new information. However, as we move into more complex applications, we find that real-world problems often present us with a different kind of challenge. In many scenarios, we don't start with the initial conditions. Instead, we observe a result or an outcome first, and our task is to work backward to deduce the original cause. This shift in perspective, moving from an observed effect back to its potential origin, is exactly what we call reverse probability. Over the next few slides, we will break down the difference between forward and backward reasoning and see how we can use tools like Bayes' Theorem to solve these puzzles. Understanding forward probability. Now, before we dive into the complexities of reverse probability, we need to make sure our foundation is solid. To truly grasp the reverse concept, we must first be very clear about what we call standard or forward conditional probability. Think of a forward scenario as a straight line of logic. We start with a known source or a known cause, and our goal is to predict a specific outcome. In terms of the underlying logic, we are asking ourselves, if we know that a specific condition, let's call it E, has already occurred, what is the probability that event A will then happen? In mathematical notation, we write this as P of a given E, which you can read as the probability of A given E. To make this concrete, let's look at an example of this forward reasoning. Imagine you have 2 bags of marbles in front of you. Bag 1 contains 3 red marbles and 2 white marbles. Bag 2 contains 2 red marbles and 3 white marbles. Now suppose I give you a piece of certain information. I tell you, you have definitely selected bag 1. If I then ask you, what is the probability of drawing a white marble? You are performing forward probability. Why? Because the source, which is bag 1, is already known to you, and the only thing you are trying to figure out is the unknown outcome, which is the color of the marble. Keep this cause-to-effect flow in mind, because in the next slide, we are going to see what happens when we flip this entire process on its head. Understanding reverse probability. As the name suggests, reverse probability flips our entire perspective. Instead of starting with the cause and predicting what the effect might be, we do the exact opposite. We start with an effect that we have already observed, and we work backward to try and determine which cause was the most likely culprit. Let's look at the underlying logic here. Imagine we observe that an event, let's call it event A, has already taken place. Our goal now is to calculate the probability that this event was triggered by a specific condition, which we will call E sub I, out of all the various possible conditions that could have caused it. In mathematical notation, we write this as the probability of E sub I given A, which you would read as the probability of E sub I given A. To make this concrete, let's return to our marble bags from the previous slide. Remember, bag I had 3 red and 2 white marbles, and bag II had 2 red and 3 white marbles. In our forward example, we knew the bag and looked for the marble. But now, let's try reverse reasoning. Imagine you are blindfolded. A bag is chosen at random, and a marble is drawn. You take off the blindfold and see that the marble in your hand is white. The question we are now asking is, given that this marble is white, what is the probability that it actually came from bag II? The outcome is now a known fact. Notice the difference. In this scenario, the outcome, the white marble, is known, but the source, whether it was bag I or bag II, is the unknown we are trying to solve for. This specific type of backward reasoning, where we move from an observed effect back to its potential cause, is exactly what the core objective of Bayes' theorem is all about. We will be using this theorem to solve these types of problems in our upcoming slides. Now that we have a clear grasp of how forward probability works, where we start with a known cause to predict an outcome. Let's shift our focus to slide 3, where we explore the concept of reverse probability. Step-by-step comparison. Now that we have looked at the individual definitions of forward and reverse probability, let's bring them together to see the difference clearly. To help you distinguish between the two, I want us to focus on the direction of the flow of information. First, let's revisit the forward probability flow. Think of this as moving from left to right, from a known cause to an unknown effect. In this direction, we start with something we are certain about, the cause, and we use it to predict an outcome. For example, if we know that bag 1 has been selected, we are looking for the probability of drawing a white marble, which we write as the probability of W, given E1. On the other hand, we have the reverse probability flow. This is the backward movement we discussed in the previous slide. Here, the flow goes from a known effect back to an unknown cause. In this scenario, we start with the observation that a white marble has already been seen, and we are working backward to find the probability that it specifically came from bag 1, which we denote as the probability of E1, given W. By looking at these two flows side by side, you can see that the starting point and the end goal are essentially swapped. Keeping this distinction in mind is crucial, because as we will see in the next slide, confusing these two directions is one of the most common mistakes students make when first learning this topic. Common mistakes to avoid. Now, before we move on to our final summary, I want to pause here and discuss some common pitfalls. As you begin working with these types of problems, you'll find that beginners often stumble upon a few specific errors. The first, and perhaps most frequent mistake, is confusing the probability of a given B with the probability of B given A. It is very tempting to assume that the probability of white given bag I is the same as the probability of bag I given white. However, as we discussed in the previous slides, these are fundamentally discretely different questions. To see why, let's look at the math. The probability of W given E1, that is, the probability of drawing a white marble given that we are looking at bag I, depends solely on the contents of that specific bag. But the probability of E1 given W, the probability that we chose bag I given that we have already seen a white marble, is much more complex. It depends not only on the contents of bag I, but also on the contents of all other available bags and the initial probability of picking each bag in the first place. The second mistake to avoid is ignoring other possibilities. In reverse probability, you cannot look at one source in isolation. If you are trying to find the probability that an outcome came from bag II, you cannot simply look at bag II's contents. You must also account for the possibility that the outcome could have originated from bag I or any other bag available in the experiment. You have to consider the whole picture to get the correct answer. Keep these distinctions in mind, because understanding this nuance is exactly what leads us into the mathematical tool we will use to solve these. Bayes Theorem. Key takeaways. First, let's revisit forward probability. As we discussed in our earlier examples with the marble bags, forward probability is all about prediction. It is the process where we start with a known source or a known condition and use it to predict what the outcome will be. On the other hand, we have reverse probability. This is the backward reasoning we explored in slide 3. Here, we don't start with the cause. Instead, we start with an outcome that we have already observed, and our goal is to work backward to identify which source or cause most likely produced that result. To help you remember this, think about diagnostic reasoning. This is a perfect real-world application of reverse probability. For instance, in medicine, a doctor observes an effect, like a specific symptom, and then uses that observation to work backward to diagnose the underlying cause or the disease. Finally, it is crucial to remember that while the logic of moving from effect to cause is intuitive, the actual calculation requires a specific mathematical framework. The powerful mathematical tool we use to perform these reverse probability calculations is known as Bayes' theorem. All right, we have reached the end of our lesson, so let's take a moment to summarize everything we have covered today to ensure the core concepts are clear. In our next session, we will dive deep into the formula for Bayes' theorem and practice solving complex problems using this method. Well done today.